Hi everybody, welcome to another video in Business Calculus, section 11.2, second derivative and graphs. On the previous section, we learned that the first derivative gives us the critical values. We let it equal to 0, does not exist, and we check in the domain. And after that, the derivative tells us where the function is increasing, where the function is decreasing, and from there we can locate the local maximum and local minimum. This section we learn the features that the second derivative will tell us. So first we have concave upward, or just concave up, and concave downward, or we call in general is concavity. The graph of the function is concave up on an interval if the derivative is increasing. So again, increasing is where derivative is positive, so we have derivative of the derivative. Naturally, derivative of derivative is second derivative. So the way we define it is the derivative is increasing, that is concave up. Derivative is decreasing, this is concave down. Notice that it is the derivative, not a function. And once again, increasing is where derivative is positive, decreasing is where derivative is negative, and we have derivative of the derivative. Therefore, we will talk about the second derivative. Right, the notation is double prime, or we write like that. If we write it out, this will be y, sorry. So for example, if we write, this is derivative with respect to y. Now, if we want derivative of derivative, and multiply them out, kind of, we have d square and dx square y. Right, so that is the notation of derivative. All right, now let's go back to, we still go back to the graph. What is the second derivative? Tell us what is actual concave up or concave down. Well, concave up is something like this. Concave down is something like that. So how can we tell if it is concave up or concave down, especially where we don't have that? What if we just have the part of the graph that only go from this? How can we tell if it is in concave up or concave down? Well, the way to determine that is if we draw the tangent line to the graph. If the tangent line is below the graph, then it is concave up. If the tangent line is above, it is concave down. So I will write tangent line below the graph. For now, space, so that's all I can write. So that is concave up. Tangent line above is where concave down. Right. So when we have this part of the graph, we just draw the tangent line at some point. As you see, it is below the graph, therefore this one concave up. Or we think about this, if we have a line, if we bend it up, like we bend it that direction, that concave up. If we bend this direction, this is concave down. So that one is up, and this one is down. So we're bending from the straight line. Right, so that is the graph and concavity. Now in terms of derivative, in particular second derivative, what can we say about it? Well, it's easier. We say it is concave up if the second derivative is greater than or equal to 0, and concave down when the second derivative less than 0. the way I remember it is this is second derivative, right? When it's positive or when it's greater than 0, it is concave up. And second derivative is negative, it is concave down. Right. There. Concavity and second derivative. Right, now let's look at the first example. Find the intervals where the function is concave upward and those where the function is concave downward for the following function. So that is a function. So simply enough, just find the second derivative. And if it is positive, concave up, negative, concave down. Now just go back to just like the previous section. There are 4 possibilities. We need to take care of when it is equal to 0, when it is undefined, then we have positive or negative. So we find second derivative, making it equal to 0, does not exist. We don't call that the critical values. If we call that anything, probably we can call it partial partition number for second derivative. Right, let's call it that. Right, so we find the interval where the function is concave up or concave down. So first, we need to find the second derivative, but I just say find the partition number. For the second derivative. Right, so naturally we take the second derivative, but first the first derivative, 3x squared minus 18x plus 24, and then find second derivative, which is derivative of that again, give us 6x minus 18, and that's it. Now just like previous section, we let it equal to 0 and does not exist. Right, we don't have fraction here, so we just say that equal to 0 plus 18 divided by 6, so have x equal to 3. And does not exist. This is the function polynomial that is defined everywhere, so there will be none. So we have that. And they will say, why don't we put it back into the function? Of course we can, but notice that in this problem we only find the interval, so we really don't care what happened at the point. So we don't need to do that. So we find the partition number for second derivative. Next we find the sign chart for the second derivative. Again, the sign chart. So this is pretty much like what we did on the previous section, except we use second derivative instead of the first derivative. There's only one partition number for second derivative, and the second derivative is 6x minus 18, and when x equal to 3, the second derivative equal to 0. Right, decimal I choose 0 and 4. Put 0 in for x, we have negative 18. And put 4 in x, that 24 minus 18 is 6, so it's positive. That is the second derivative. We can say that the function negative on the second derivative is concave down, positive is concave up. The conclusion we will write where the function is concave up, we say concave up. On the interval of 3 to infinity, and concave down on the interval. Where's the negative infinity to 3. Right, so that's simple enough. Just find second derivative equal to 0 does not exist. This problem only asks for the interval, so we really don't need to figure out what actually the point is. If we need to know what the point is, then we worry about that. But this problem asks for the interval, so don't need to do that. Right, next we have this function. Once again, find the interval where the function is concave up and concave down. So meaning we will take the second derivative. I will rewrite this as x plus 9 to x to the negative 1. Right, now with that we can find the derivative and then second derivative. So the first derivative is equal to 1 down that negative 9 x to negative 2, and then second derivative of 1 is 0, that gives us negative 2 times negative 9 is 18 x to negative 3, and we can move that to the bottom. (18/x cubed). Right, then we make it equal to 0 does not exist. This time we do have a fraction, so equal to 0 is where the top is equal to 0 and does not exist is where the bottom is equal to 0. Right, on the top we only have 18 and that's not equal to 0, so we do not have anything on that side. On this side, x cubed, the bottom equal to 0, then x must be equal to 0, so we only have 1 point. Once again, those are partition number for second derivative. So let's say the first step, find partition number for second derivative, and then we just go to the sign chart for the second derivative. As mentioned on the previous problem, we do need to worry about the domain of the problem. Here we divide by x, so the only thing we need is x is not equal to 0, because if x equal to 0 is undefined, so the domain is everything but 0. Partition number though, we have x equal to 0, so right, second derivative is 18/x cubed. Right, and when x equal to 0 it does not exist. Right, that's point. Let's put something negative and positive. Put negative number in here, 18 negative 1 cubed, so that's negative, and put positive in there, that's positive, and negative is concave down. Positive is concave up. So we say concave concave downward on negative infinity to 0 and concave up on 0 to infinity. Pretty straightforward. Right. Now, as mentioned before, we don't really know, we really don't need what happened at 0. The function is undefined at 0, by the way, but we don't need that. We only need the interval where there's concave up and concave down, and that's all we do. The sign chart for second derivative. Right, next, we have inflection points. An inflection point is the point on the graph where the function change the concavities. So we can have from concave down to concave up. There is an inflection point here where it is concave down followed by concave up, or could be the other way around. Inflection point is where it changes from concave up to concave down, or from concave down to concave up. Those are the inflection points. Now, in terms of second derivative, it said if y is continuous and it has inflection point, then either second derivative equal to 0 or does not exist. Well, we have been doing that all along, right? So in this case, if there's a point here, that would be the inflection point, but that point does not exist, so no inflection point there. On this one though, when x equal to 3, the function suddenly defined, so we have concave down and then concave up. So there is an inflection point at 3. Right? So derivative equal to 0 does not exist, but it have to change the concavity. By definition, inflection point is where concavity changes from down to up or from up to down. Right, now, find the inflection point for this function. Well, that of course we find a partition number, do the sign chart to see if the concavity changes or if the second derivative change the signs. So first, find partition number. For the second derivative. Right, now first derivative 3x squared minus 12x plus 9. And then second derivative 6x minus 12. And we have second derivative equal to 0. Second derivative does not exist. Alright, so 6x minus 12 equal to 0 plus 12 and divide by 6, and then that is defined everywhere, so there's none here. So that's the first step, find the partition numbers. And second step is the sign chart. We do need to make sure that the concavity actually changed, yes, meaning the second derivative will change the signs. Right, so we do need to make the sign chart for second derivative. Just make it clear for second derivative. Right. only have one pawn, x equal to 3. Right, and the second derivative we have is 6x minus 12. When x equal to cannot even divide. When x equal to 2, the second derivative equal to 0, and we divide like this. So have use the test point, put 0 in, it is negative, and put 3 in there is positive. So we actually have the change in size of second derivative, meaning it changed the concavity. Right. So because the concavity changes, there is inflection point at 2. If when we substitute in 2, the function does exist. If we put 2 in there, the function does not exist, then we really don't have the inflection point, right? Just like this, if we put in 0, it is undefined, so there's no inflection point. Even though concavity changes, we still don't have the derivative equal to 0 or does not exist. Because if it does not exist, it's 0, the function is undefined. Remember, inflection points, every time we refer to points, we mean a point on the graph. And if it is on the graph, it must be in the domain of the function. So, whatever the point we have in partition numbers, make sure it belongs to the domain of the function before we do anything. Right, in this case we do need to evaluate at x equal to 2. Then what do we substitute in? Remember, we're looking for inflection points. Every time we talk about points, we mean the point on the graph, which means it have to be in the domain. Right, so just choose down to x and just type that function in. X cubed minus 6x squared plus 9x minus 1. Right, so that is equal to 1. So because concavity changes, the function is in the domain, and concavity changes mean the second derivative change the sign as well. So with that point exists and concavity change the sign, so we have inflection point. When x equal to 2, the function equal to 1. So that's how we find the inflection point. Just find the second derivative, make it equal to 0 or does not exist. And it is a point, so make sure we substitute in the original function and we have the point. Right, next, also find the inflection point for this function. Right, now remember we talk about ln of something. If we put a negative number or 0 in here, it will be undefined. By the way, the x squared minus 4x plus 5, if we graph, you see the graph is always above the x-axis, meaning this one always positive. So the domain is all real number, so that's good. We don't have to worry about the domain is anything less than in negative infinity to infinity. For this problem, the sign chart will go from negative infinity to infinity. Right. Now, derivative. By the way, this looks like a long problem. Right, so the derivative. This is the derivative of ln of something is the reciprocal of that thing, and derivative of that. We're going to put x squared minus 4x plus 5, x squared minus 4x plus 5. Right, derivative of this is 2x minus 4. And we have x squared minus 4x plus 5. Now we find the second derivative, and for that we will use the quotient rule. U is 2x minus 4, v is x squared minus 4x plus 5, u prime is 2, and v prime is 2x minus 4. So second derivative, I'm going to write the quotient rule. U prime v minus u v prime over v squared. Alright, I will multiply them out and simplify. To x squared minus ax plus 10. I multiply them out first. For x squared minus ax minus another ax plus 16. Right, keep going. Remove the parentheses and then combine like terms. Right, 2x squared minus ax plus 10 minus 4x squared. That negative 16x, and not a negative, that plus 16x. And then negative 16, that minus 16. Right, combine like terms. Two x squared minus 4x squared minus 2x squared. 16 minus 8. 10 minus 16. Right, so we have the second derivative. Now first we find partition number. For the second derivative, for that we'll let second derivative equal to 0, meaning the top is 0, and derivative does not exist, meaning the bottom equal to 0. Right, negative 2x squared plus ax minus 6 equal to 0. I will divide everything by negative 2. X squared negative 4x plus 3 equal to 0. Here we can use quadratic formula or factoring, doesn't matter. b squared minus 4ac over 2a. Right, so we have 4 plus or minus negative 4 squared 16 minus 12 4 squared 4 is 2 over 2. Right, 4 plus 2 divided by 2. 6 divided by 2 is 3. 4 minus 2 divided by 2. That is 1. So you have 3 and 1. On this side we have the bottom equal to 0 where the second derivative does not exist. If the square equal to 0, then without the square must be 0. We run out of space here, but if we're going to solve for it using quadratic formula, what do you think we will get? I said I've run out of space here. But on this side, if we do that, remember the graph like this. So what it means is there's no x-intercept, so no solution. So what we get here is imaginary. So here we just have imaginary. So that means we only have 3 and 1. Right, I think that's enough to draw the sign chart here. Right, we have 1 and 3 partition number, and the second derivative is remember that and we have x squared minus 4x plus 5 squared. Right, when x equal to 1 or 3, the second derivative equal to 0. Alright, test point I will choose 0, 2, and 4. I'm just going to use a calculator on this one. Right, derivative negative 2x squared plus ax minus 6 divided by x squared minus 4x plus 5 squared. Right, let's look at the graph. Sorry, we don't need to look at the graph. We need to look at the table. Right, is right like that. Make sure we enter it correctly. Right, second delete to insert. Negative 2x squared plus ax minus 6 divided by x squared minus 4x plus 5 squared. Go to table. At 0 we have negative. At 2 we have positive. And at 4 we have negative. So concave down and then up and then down. And of course in that case there will be the inflection point here and there. So inflection point occurred x equal to 1 and x equal to 3. Of course we put it back in the original function, we have the point. But run out of space. So that's what we can see is the inflection point there. The function is always defined because the argument of the log is positive. We did check that. Right. The last part of the section is is the point of diminishing returns. So it is defined to be point of diminishing return is where the rate of change, which is derivative, go from increasing and decreasing. Derivative is increasing, so that is concave up and concave down. So pretty much inflection point is going from this to that, and the point of diminishing return is this point where it goes from concave down to concave up. I'm sorry, concave up to concave down, always concave up to down, because where the rate of change is increasing, decreasing. Right, so where is significant of that? So when we get on the left side of it, or when we go close to it on this side, on the left side, it increases very fast. If we go close to the point of diminishing return, but when we pass it, it's still increasing, but it will be very flat. So that means in terms of business, let's say we run an ad campaign for example. When we get close, we try to put a lot of money to increase the ad, so that the sale will increase. But when we pass that point, even though we can put a lot of money in, even though the sale may increase, but it will not be by much, because after that point the increasing gets smaller, eventually go to decreasing. So the point of diminishing return is it's good that we always want to be very close to it on the left hand side, because that is where it is increased, the rate of change is increased at the highest. And in sale or in business, we want the rate of change to increase at the highest. Right? So remember, inflection point is only shown in this case, meaning we only go from the second derivative negative to second derivative, sorry, up to down. So we need the second derivative positive and then negative. Right, so that is where we have the point of diminishing return. So we have this example. Currently a discount appliance store is selling 200 large screen TV monthly and want to put X thousands of dollars in advertisement. The ad company estimate the sale will be this. Find the point of diminishing return. So it is before we get to the point of diminishing return, we want to put more money to increase, to get close to that. But when we get to that point, we will not want to put any more money to it, because when we get past that point, it will be very difficult to increase the sale or increase the revenue after that point. All right, now in terms of math, that will be easy. Set derivative, find derivative, and then derivative again, and find partition number for second derivative, and then the sign chart. And notice that it only goes from concave up to concave down for it to be the point of diminishing return. Right, so let's do that. We have the function. Now we find the derivative and second derivative. The derivative of this is 9x squared times 4, so that 4 times 0.25, so that's conveniently x cubed and 200. Derivative constant is 0. And then we'll take the second derivative. That gives us 18x minus 3x squared. Alright, so we have the second derivative. First we'll find partition number. For the second derivative. So that means it is equal to 0. Or does not exist. So equal to 0. Here we just factor out 3x. that gives us 6 minus x, right? 18x minus 3x squared equal to 0. So 3x equal to 0, or 6 minus x equal to 0. So have x equal to 0 or x equal to 6. Right, second derivative, of course, does not exist. This is a second derivative. It is defined everywhere, so we do not have anything there. Right, next we will have the sign chart. The sign chart for the second derivative. Right, one thing we note that in this case we do not have the whole interval, because x was x. X is thousands of dollars in advertisement, and it cannot be negative. That makes sense, right? And go up to 9 of equal to, so bracket at 9. So that's what we have. Right, and then with that we have 0 and 6, because 0 right on the boundary. We not really do that. We only consider the 6, because if x equal to 0, yeah, it is. Remember, we need concavity to change sign, meaning we need something on the left of that point and something on the right of that point, right? It's on the edge. There's can only be points on the right. There's nothing on the left. So 0 cannot be the point of diminishing return. It cannot be the inflection point, because inflection point have to be in the middle, where it change from concave up to concave down, or concave down to concave up. So there must be some point on the left and some point on the right. With that, the boundary cannot be inflection point. Right, second derivative. 18x minus 3x squared. Alright, for 6, I choose 1 and then 7. And when x equal to 6, second derivative equal to 0. So put 1 in here. I'm just going to put the second derivative. 18x minus 3x squared. And just go to the table. When x equal to 1 is equal to 15 positive. And when equal to 7 is negative. So we have concave up to concave down. And so on the graph we do have concave up to concave down. So we do have the point of diminishing return at 6, right? Remember, it's only this direction. The other direction is not. If you go like this, it is not point of diminishing return. Sorry, I'm confusing myself. Again, if it increasing, if it go like this, it is not the point of diminishing return. It have to go from down, from concave up to concave down. This is not. This is concave down to concave up. It's not the point of diminishing return. It have to be concave up to concave down. So point of diminishing return is at 6. And if we want to, we can put 6 in the original number. Right, I'm going to put 6 in the original function. Remember, original function, if we want points. Right, 6 turned to x. And now we have 3x cubed minus 0.25 x to the 4th plus 200. Right, that's 524. So the point of diminishing return is x equal to 6, in that case $1,000, and estimate the sale will be 524 flat screen TVs. Right, so not only that is the point of diminishing return. If we at the moment we're not spending that much, we might want to spend close to 6, because in that case that gives us the most increasing. When we get past 6, the more money we put in will not result in the number will not be as advantage, because after this it is still increasing after that, but the rate of increasing gets smaller and smaller. So we might invest money, but it will be very difficult, more difficult to increase the revenue or increase the sale. So that's why we said the point of diminishing return is at 6. In this particular problem, $6,000 is the amount of ad that we want to spend, and with that we have the sale of 524 flat screen TV. Right, now with that we finish section 11.2. As always, thank you for watching, and see you in another video in Business Calculus.